We're going to take a look at some sample simple probability problems, 4 different types. So, starting with theoretical probability, we want to know what is the probability of getting a sum of 7 if you roll 2 number cubes. So, we're looking at the P of 7, and we need the number of ways to get a 7 over the total number of outcomes of 2 rolls. So, we can roll a 1, 2, 3, 4, 5, or 6 on each die, and we're going to set up a little table to show us what the results of rolling each of these combinations is. So we have a 6 by 6 grid, so we have 36. That's our denominator, the total number of outcomes. So we can get a 2, 3, 4, 5. Ah, there's the 7 we're looking for. 3, 4, 5, 6, another 7. So there's a pattern. This whole diagonal here is going to be full of 7s. So M is 6. We have 6 out of 36. 1 out of 6 are about 16.7% chance. So we can also use this table to figure the theoretical probability of rolling doubles, or perhaps the probability of rolling snake eyes, which is 2, 1. Other games of chance might require us to use combinatorics. For instance, what's the probability of getting 2 7s in a 5-card hand? So our probability is M over N, equally like the outcomes over sample space. So we need the number of ways to get a 7 over every possible hand. So here's 2 cards. We want them to be 7s, and the suit doesn't really matter. So what we're going to have to do is 4 7s in the deck. We want 2, 4, choose 2. Now we have 3 non-7s, and we need to figure out how many different possibilities there are there. So we have 48, choose 3. That's the number of combinations of the remaining cards. So our probability is going to be these 2 probabilities multiplied together as the numerator, and then how many different hands are possible with 5 cards. Well, there's 52 cards in the deck. We're going to choose 5. And that's going to be our denominator. So we work these out on a calculator. We have 6 times some numbers there. We're going to end up dividing those and getting about 0.039, or around 4%. That probability would be the same for any pair. Some problems require us to use Venn diagrams in order to organize the information. So let's say we have a school, and in the school some students are pirates, and some students are ninjas, and some students are pirate ninjas, and everybody's one of these things. So we have 95 pirates, we have, 73 ninjas, we have 52 pirate ninjas. You would think the number of people who go to school is 95 plus 52 plus 73, or 220, but that's incorrect. See, the problem is we can't think of these as 3 separate groups. Many people say, oh, there's a group of pirates, and there's a group of ninjas, and there's a group of pirate ninjas, and they're exclusive. The thing is, the pirate ninjas actually belong to both the groups of pirates and the groups of ninjas. So if we have 52 pirate ninjas, that comes from both those other groups. That includes people who are just pirates, which there's 43, or just ninjas, of which there is 21. So we have to make sure that we account for any groups that may be overlapping. Now, if we look at the number of people who are going to our school, it's 43 just pirates and 52 pirate ninjas, 21 ninjas for 117. We're going to use that as a denominator for figuring, say, a probability of people being ninjas only. We have 21 ninjas only over 117 total people, 7 out of 39. That's going to work out to about 17.9% probability that a student is just a ninja. We use the Venn diagram to determine overlapping groups in our sample space. For our 4th and final example, we're looking at geometric probability, and this is using areas to find a theoretical probability. So let's say we've got a space like a checkerboard, and it's 64 equal area squares, and half are black and half are red. It's the same as if we had any space where half were black and half were red. If we're looking at the area, it is 50% red and 50% black. So we have an event like, say, this pigeon, and the pigeon is going to go drop a pebble on the checkerboard. Okay, fine. Pigeon's pooping on the board. So the probability of the event occurring in either color is the same as the amount of area that color takes up out of the total area. So you can poop on red 50% of the time, poop on black 50% of the time. The probability of any event is based on the area of the event over the total area. So let's do away with pigeons and checkerboards and look at geometric probability in another way. Say we have a dartboard, and it's a very simple dartboard. It's got a radius of 9 units, and the bullseye is 3 units. We can find the area of either circle using pi r squared. So the area of the bullseye is pi 3 squared, or 9 pi. The area of the whole target, including the bullseye, is 81 pi. So the geometric probability of a dart or a pigeon striking the bullseye is 9 pi over 81 pi, or 9 over 81, or 1/9, or about 0.1 repeating, or 11.1%. So the probability of it not being a bullseye would be the area that's not a bullseye over the total area. So we subtract the bullseye from the total area and divide that by the total area. Pigeon, what are you doing? Pigeon? Fine. Geometric probability. Area of the event over total